All right. So again, thank you for showing us some options with the IEEE group here in UNO's campus. Today, excuse me. Today we are continuing, or we're starting on the next module. Module 6, the error handling, pointers, pass by reference, and more formal unit testing will be throughout this week. So that's your lab today and your hack tomorrow. And next week is when you'll be we're actually starting to work on arrays. I mention that because the midterm is also coming up. The midterm is worth 100 points, about double what your exam was. It'll probably be the exact same format as before, but it will cover everything up to and including arrays. So as we're talking about arrays here, know that that will be on the midterm, and that will be that'll be the end of the midterm essentially. I just made to make sure that everything is working here. Yep, we're good. All right, so what are arrays? Well, arrays are collections of things, right? It's really rare that you're going to deal with one piece of data, one number, or one character or whatever, right? You can store multiple pieces of data or numbers or whatever you're doing in a collection, right? And in C, the collection, the collection that we use in C, in C you use arrays to do this. I got tripped up there because you should understand that many programming languages have a lot of different collections. For example, Python has lists, sets, and dictionaries. Most programming languages will have a much richer library of data structures like that with different ways of storing things. But unfortunately, with C, it's bare bones. What we're going to be looking at is just regular old arrays. In C, you use arrays to store elements of a similar type. In other words, if you've got an array, it's only going to hold integers. If you've got an array of you can have an array of doubles, and it's only going to hold doubles. Right? You have to have similar items. There are languages that support mixed types, where you can have an array or a collection that holds integers and doubles and strings and whatever else you want to put in there. But with a strongly typed language like C, or a statically typed language like C, if you have an array, it only holds elements of one type. Okay. So what is an array? Arrays are ordered collections of variables of the same type. In other words, when I say ordered, I don't mean sorted. Sorted is different than ordering. If I have, say, elements 10, 20, 30, those are ordered and they're sorted. But if I had 10, 30, and 20, right, those are still ordered in the sense that there's a first one, the first one being 10, the second one is 30, the third one is 20. It's not ordered. It's not sorted, though, is it? Right? No, it's just ordered. And that's what we mean by arrays are ordered. There's a first element, there's a second element, there's a last element, right? Arrays have one single identifier. That is the name of the variable. And you can access individual items, or elements, I should say, in the array using an index, or an indices is the plural form of that, right? The index is specified using the square or bracket notation. Right? So, for example, the first element is at, if we have an array called ARR, the first element is at ARR sub 0. This is referred to as zero indexing, right? Zero indexing. The first is at index 0. We don't start our accounting in computer science at 1, right? Grade schoolers will start their counting at 1, 2, 3, 4, 5. But very, very quickly you learn that you need 0 in your counting because you got to start somewhere. Likewise, in computer science, the vast majority of programming languages are going to be 0 indexed. We'll understand why later on. It's about how memory works, essentially. But there are a couple of exceptions. In the other classes, I was talking about how I was a reviewer for the AP Principles exam. I wasn't grading exams. I was actually reviewing the exam over the weekend. And I noticed that they had a bias towards a programming language called Scratch, which is common in some high school curriculums for AP advanced placement. Did anybody ever play with Scratch when they were in high school? All right, a few of you. That one is actually one indexed. And unfortunately, the AP exam that they chose to use was one indexing, where the elements in a collection start at 1. So if you've got 5 elements, it's 1, 2, 3, 4, 5. In my review, I pointed out that that's kind of a bias towards Scratch. And if you're using Python or any other programming language in a high school curriculum, Java typically, or again, Python, you're not going to have that same experience. You're going to be starting with 0 indexing. So keep that in mind. A small minority of programming languages don't do this. All right. The other one that I'm thinking of that you might have seen before is, anybody do any Roblox programming? All right. What programming language do you use there? Lua, right? And Lua, where do they start their indexing? Don't remember? 1. Right? So those are the 2 exceptions. The third exception that you might have seen before is MATLAB, if you've ever played around with MATLAB. But the vast majority of programming languages that you're going to see throughout your career are going to be 0 indexed. The first element is at 0, the index 0. The second is at array sub 1. Right? The third, right, following this pattern, is at array sub 2, etc., etc. There are no gaps. Each one exists right after the other. They're all contiguous. They're all together. Right? You can use a variable as an index. For example, you can go, I want the ith element. ARR sub I, right, is the ith element. And now we know why in for loops we've been using I, right? Int I is equal to 0, I is less than n, I plus plus. What does the I stand for? Index. That's the idiomatic for loop that we're going to write here in a moment, okay? If there are n elements in an array, the last one is at index what? N minus 1. Good. Right? Remember, we start at 0. So if there are 5 things in there, 0, 1, 2, 3, 4. Because we're starting at 0, we're always going to end 1 less than the size of the array. Okay? So let's go ahead and jump into it with something that are with an example examples that are called static arrays. Static arrays are arrays that are of a fixed size and allocated on the program stack. So do we remember what the program stack looks like? Function calls function, calls function, calls function. A stack frame, a new stack frame every time this happens is created on top of the stack. It's pushed on top of the stack. That function calls another function. That creates another stack frame, etc. Right? We will quickly we will quickly abandon static arrays. And we'll find out why here in a second after we've looked at how to use them. Let me jump over to my coding environment over here. And let me just go ahead and create a static array. I'm going to create a static array that can hold, say, 5 integers. Okay? If I create int x, that creates one variable, one integer variable. I don't want that. I want an array of variables. So I'll just go ahead and call it ARR here, short for array. And I will specify, using the square bracket syntax here, how big the array is. This array can hold 5 elements, right? At most. It holds 5 elements, period, right? There's the first element, second, third, fourth, and fifth. And you can go ahead and start setting the values here. Array of 0, I'll set that first one equal to 42. Array of 1 is equal to 101 is what I've been using. And let's go ahead and set the last element here. The last element as at what index in this example? 4. Okay. And I'll set that equal to 109. There we go. I can iterate over this array. For int I equals 0, I is less than 4, or 5, excuse me, I plus plus, printf, array of %d is equal to %d. I'm going to print out both the value stored in the array and its index. So index and then the value stored in the array using that square bracket syntax there. Right? Let's go ahead and compile this and see it run. GCC demo. All right, there we go. But before I run this, predict what the second and third elements are. Did I actually set those? Nope. So let's go back to a single variable here. What value is stored in X as of line 10? Garbage. Could be 0. Could be garbage. It could be dead beef, right? It could be whatever, right? There is no defined default values in C. Likewise, with an array, there are no defined values for default values for elements in an array. Now, I am willing to bet, more than I would be willing to bet on the Husker game this weekend, that those two values are going to be 0. But that's just because it's the compiler coming in and setting those equal to 0. Right? If I expand this out to 5,000 elements, do you think they're all going to be 0? I'm definitely willing to bet, again, parlay this into another bet, that no, they're not all going to be 0. The vast majority of them are going to be 0. But then we get to stuff like this. What is that? Garbage. Some more zeros. More garbage. More garbage. More garbage, right? Garbage all over the place. Lots of zeros, but otherwise just pure garbage, 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 garbage. Right? If you have an assumption on what's stored in an array without actually explicitly storing something, then that assumption is not correct. Right? We just got away with it because it was a very small array and there just happened to be 2 zeros in there. Okay? All right. So, some observations here. Let me actually go ahead and grab this code before we get rid of it and work on something else. There we go. That'll be in the notes for you. Here's some observations. There are no default values defined in C for any variables, including the contents of an array. Right? It could be 0. Could be 0, could be garbage, etc. Right? So make no assumptions about what's stored in there. Okay. Once you've created an array, you can use the square bracket syntax to access or set the contents, the elements of an array. Right? Okay. What about some pitfalls here? Pitfalls. What happens if you attempt to access elements outside the array? For example, what if I did this? Remember that my array is only of size 5. Does the negative first element exist? Hopefully we'll get a segmentation fault. We'll find out here in a second though, right? If I've got 5 elements in there, 0, 1, 2, 3, 4, what if I went to 5? Right? What if I did those two things? Let's experiment and find out. Okay? Keep working. Yep. All right, let's go ahead and do arrays of -1 is equal to, I don't know, 1,000. Right? And arrays of 5, we'll set that equal to 10,000. There we go. Right. Let's find out. And, in fact, what I'm going to do is I'm going to copy these and print them. Right. I won't put them in my for loop, my idiomatic for loop here, because I don't want that. I don't want to change my loop. I'm just experimenting here to find out what happens when I screw something up. Okay? GCC. Did the compiler catch it? Nope. Would it catch it if I turned on all the warnings? Nope. Right. You're good to go, apparently, for as far as the compiler is concerned. Let me go ahead and run this. Right. Ah, it kind of worked, right? Except that I set it to 1,000, but it says it's 5. Right? So weird results there, right? But I did set 5 to 10,000, and that seemed to work. No segmentation fault here whatsoever. So maybe you can do this, right? Now, what am I doing here? Let me go ahead and grab this, and let's take a look at I actually don't even know if this is going to work in this visualization tool here. Let's find out. Let's visualize this. Before we visualize this, let me go ahead and comment out the bad code or the code that we think it is bad, right? And let's visualize how this is actually working in memory here. We've got a stack frame representing main. Within that stack frame, I've got my array, elements 0, 1, 2, 3, and 4. Let's walk through this code as we set these elements. The first one gets set to 42. The second one is 101, and then the last one gets set to 109. Tell me again, what values are stored in 2 and 3? Exactly, question marks, right? They are uninitialized values. In fact, in this simulation, when I attempt to actually print these out, I print out 42, I print out, print out 101, and then when I try to print out something that is uninitialized, it stops and tells me, wait a second, it's uninitialized, you might need to fix this. That didn't happen over here because the operating system was like, well, you do what you feel. It's your memory, go ahead and screw it up as much as you want, right? Over here, it was being a little bit kinder and saying, you might want to rethink what you're doing. Let me go ahead and edit this and restore those two bad lines right there, okay? And let's visualize this execution. Remember, does the -1th element exist? Does the 6th element at index 5 exist? No. Think of this as a tabletop. If you go too far to the left, you'll fall off the tabletop. If you go too far to the right, you'll fall off on the other end, right? So when you attempt to do something like this, I'm sure that it's going to be an error here, and attempts to do that, well, oops, hey, cool. It was complaining before about that other stuff, but it's not complaining about this. So be it, right? Weird, but okay. It is going to complain that you didn't set to, but whatever, right? Just because you don't see anything go wrong doesn't mean that there's not something that's going wrong. It's just not manifesting itself as an actual segmentation fault or an error, right? Certainly it's wrong because we set that equal to 1,000, not 5. I wonder what's going on there. We're just corrupting our own memory, right? We're corrupting our stack frame right here. Our nice stack of dishes. It doesn't matter if those are clean dishes or dirty dishes. The operating system doesn't care. You can go ahead and break your own dishes as much as you want. They're your dishes, right? That's your memory. You can go ahead and corrupt your own memory as much as you want. So even though it didn't show up as a segmentation fault here, there is still a tool that we could use to detect that we're doing something wrong. What was that tool that we looked at on Friday? Valgrind. Let's look at Valgrind and run our program through that. We get, wow, even though it didn't look like it, there are 10 errors here, right? There's a lot of stuff that's going on. And again, I didn't compile this so that all the line numbers would be preserved, so it doesn't know exactly what happened and where. But if I did, remind me how I do that. How do I compile so that I can get Valgrind to remember everything? -G. Right? And when I run that, I get a much, much better report here that tells me I'm doing something wrong at various spots in the program here. Where is it? There we go. Where is, let me clear this out and run it again.
How do you clear that?
Command K on Mac. Windows, I imagine it's going to be Control K, right? Or you can type clear, right? But it's just easier for the quick key. Right? I didn't want to clear that. Yeah, there we go. All right, so let's take a look at this report here. Uninitialized value was created on line 7, right? We set the first one, we set the second one, but we never set the third one. There should be an invalid, conditional or jump move. There's uninitialized values here. There are bad accesses right here on lines. Where is it? Well, mostly when we try to print it, but definitely it started all on line 7 here. We're getting a lot more information here. Again, it's kind of cryptic. You have to get used to reading this kind of information, but at least we know it ain't all roses, right? There are 10 errors here that we have to take care of, okay? And you can strongly look at this and say, well, yeah, that looks definitely wrong right there, right? Okay? All right, so attempts to access elements elements outside the array are we can only say that they're undefined behavior, right? They may result in a seg fault. They may result in bad output, right? It may not lead to a problem at all. You are simply corrupting your own memory. And the operating system has no problem with that. It's your memory. You do with it what you want. Remember, C is a programming language that allows you very low level access to the computer, right? It allows you to directly access memory through pointers. It allows you to go ahead and corrupt memory if you want to. With great power comes great responsibility. You're not even able to do this in a managed programming language like, say, Python or Java or something. It takes that power away from you, knowing that, well, not everybody is going to be responsible enough to use that power. It comes at a price, though. Both languages are substantially slower than C, right? And so much so that if you actually look at what's like the standard library in Python, what do you think it is? It's making system calls to the C library, right, so that it's fast. Right? So you're simply corrupting your own memory, which is perfectly fine, right? It may be a segmentation fault. It may be what's called a stack smashing event. It may simply corrupt your own memory and you're done with it, right? Another pitfall here. System stack memory is, in fact, I'm going to put that out as another bullet point here, is extremely limited. So let's come back over here and get rid of the bad things. In fact, let's get rid of all of the printing out here. And what I want to do is I want to create a really, really large array of, say, 1, 2, 3, 1, 2, 3, 5 million elements. Okay? 5 million integers. Remind me, how many bytes does an integer take? 4 bytes, right? A byte is 8 bits. So we've got 4 bytes per integer for a total of 4 times 5 million is 20 million bytes. That's just shy of 20 megabytes, okay? And I'm going to go ahead and make sure that I'm setting the last element here. 5, 1, 2, 3, 1, 2, 3, minus 1. I'll set that equal to 101 here, okay? Now, I'm not doing anything illegal here. I'm not accessing elements outside the array. I'm only accessing the first, the second, and the last element, right? Yeah, go ahead.
Do you even have enough memory for that?
That's a good question, right? Let me try to run it. So, first of all, is 20 megabytes that big of a deal? Every single one of your desktop computers, every single one of your phones has on the order of gigabytes of memory, right? I have no idea what my phone has, but I think that this laptop I'm using is using 16 gigs. I have no idea how much memory is actually available to us by using these code spaces. But like everybody's computer has at least 4 gigabytes, right, of RAM I'm talking about. Anybody have lower? Right? 8 megabytes? Or 8 megabytes. 8 gigabytes, right? Right? More. So certainly we have enough room in the computer itself. But it's still going to seg fault out. To understand that, let's look at the limits on the system. There's a utility called ulimit, which is short for user limit. Tell me about everything. And you can take a look at what all the limits are here. Right? For example, max memory size here is unlimited. Now, it's unlimited in the sense that it's going to give you as much memory as you want to use. When it physically runs out of memory, either RAM or virtual memory that's on disk, right? Then the entire computer is run out of memory, and of course it's not infinite. It's unlimited as far as the computer is concerned, but you don't have an infinite amount of memory here. Okay. But what I want to pay attention to here is that stack size. Remember the system stack here. You call a function, function calls a function, calls a function, calls a function. You are stacking those dishes. There is a limit to how many dishes you can stack, right? If you stack 50 dishes high, what's eventually going to happen? It's not stable. It's going to fall over. You will have what's called a stack overflow, right? That's where they got their name, right? That's where they took their name, at least, right? That phenomenon. And that's what we've just experienced here. What is the limit of our stack size here according to this ulimit utility? 8,192 kilobytes. That's 8 megabytes. I was trying to allocate 20 megabytes. Can I stack 20 million dishes when I can only stack 8 million dishes? Nope. It falls over, results in a segmentation fault, a stack overflow. Right? I wonder what Valgrind would say about this. There we go. Oh, wow. That's hilarious. It says 0 errors from 0 context. Why? Because the program probably didn't even load up in memory successfully. Right? It immediately died at this line right here. Right? Valgrind, shame on you. You should have seen that. Right? I mean, if it seg faults out, it should actually report why it seg faulted out. But whatever. All right. So, systems stack memory is extremely limited. Right? Usually, you are limited on the order of megabytes, right? Or even kilobytes. If you are on an embedded system, then you might have even more stringent resource measures. If you are in a very, very old system, of course, they measured memory in terms of kilobytes. You didn't have the luxury of having megabytes, right? So for that reason, we can't store anything substantial on the stack. That's why we're immediately going to run away from static arrays. Right? Instead, what we're going to focus on are dynamic arrays. Better solution. Solution, dynamic arrays. Dynamic arrays are arrays whose memory is allocated on the system heap instead of the stack. So we've got a new term here, a heap. In fact, it was hiding over here the entire time. We've got the stack and we've got the heap. When I say stack, what comes to mind? Dishes, right? A highly organized stack of dishes. There's the first dish. Right after that is the second dish, the third dish, the fourth dish. Where do you take the dish off the top? The next dish comes off the top. If you've got a clean dish and you want to put it on the pile, you put it on the top. You only access it from one direction. When I say heap, does that sound like an organized collection? No. What comes to mind with a heap? Pile of what? What? There you go. Exactly. That's what I always think of too, right? A pile of laundry. Now, if you're good, you immediately throw it into the bin and then wash it right away or whatever. But if you're lazy, what do? You have a clothes pile over there, right? And you've got this heap, which is a disorganized heap of clothes, right? A laundry. If you throw something on top of the heap, it may stay at the top of the heap. It may go down and settle in the halfway down the heap. It may fall all the way to the ground, right? It's a little bit less organized, but it's a lot bigger, right? In fact, according to ULimit, it was unlimited, right? Not that one, but one of the other, max memory size here. The heap is unlimited. You can have as much memory as you want, okay? So you pay a bit of a price for that. It's a little bit less organized, and so it's a little bit less efficient, but it's the operating system's responsibility to handle some of those details, okay? To allocate memory on the heap for use in an array, you use the how does that work? Yep, memory allocation function. There we go. As a strong hint as to what the name of this function is, I've highlighted the M and the ALLOC. So what do you think the function's name is? Malloc, exactly. And it stands for memory allocation, okay? Here's the signature. I'm just going to cut and paste that. Void star, that's something new. We'll discuss that in a second. Malloc, and it takes one argument. What is size t? You can think of size t as an integer. It corresponds to the number of bytes you want to allocate. Right? How much memory do you want? All right. So let's come over here and start iteratively replacing this thing over here. The first thing I'm going to do is I'm going to put that 5 million into another variable, so I can just use the variable and I can change it in one spot. Is that 5 million? 1, 2, 3, 1, 2, 3. There we go. Okay. I want to make a call to malloc, and I'm going to ask malloc for a certain number of bytes. How many bytes do I want to store 5 million integers? 20 million. All right, so 2, 1, 1, 2, 3, 1, 2, 3. Right? That's not the best way to go about doing that. Right? Let the computer do its math, your math for you. How many do you actually want? I want n of them. And how many bytes does each one take? What was it again? 4. So n times 4. I don't even like that because, and here's a dirty little secret of C, not all systems have 4-byte integers. There are extremely old, extremely weird systems in which an integer was 3 bytes. Right? The C standard itself says that an integer only needs to be at least 2 bytes. It can be 2, it could be 3, it could be 4, it could be 5, it could be 8. It could be anything. I don't want to have to deal with that. So instead, what I'm going to use is this macro called size of. How many bytes are in an integer? Size of int. Right? You might remember this. It was given to you in your second lab. Right? We gave you this program that output how many bytes each type took. Right? We were using size of in that entire lab. Right? If you want to allocate space for a double, size of double tells you how many bytes a double takes. Guess how many there are in a double? Not 4, but double them, right? That's 8. Where does it get its name, right? It's double in size. I want integers, though, right now, okay? So that does the math completely for me. I can take this code and move it over to another system, some weird system where it's 5 bytes, and it will still compile, and it will still work perfectly. And I don't have to hard code 4 every single time, okay? So you can use the size of macro, and it's not a function, but you can treat it like a function. It is a macro defined in the standard library to determine how many bytes each type takes. For example, size of int, size of double, right? Size of char, size of whatever. Don't hard code values. Right? Don't do that. It's a bad pattern. Okay. Upon successful allocation, I should say, allocation, successful, there we go, allocation, malloc returns a pointer to the memory it allocated for you. So if it was successful, here's your chunk of memory, right? Go ahead and do with it what you will. How does it return a pointer to that memory? Void star, right? That's something new. So malloc returns what's called a generic void pointer, right? Void star. That's weird. Let's understand it. If I was to say write int star, well, first of all, if I was to write int, that's a regular old variable. That's a regular old integer, right? What is that thing right there? Int star is a multiplication, but in the context of variable declarations, it's a integer pointer. Is an integer pointer. What if I did double star? Is a double pointer. Right? So what is a void star? We've seen void in another context. Void functions that don't return anything. This is kind of an abuse of that word because when I think void, I think nothing. In this context, though, void means anything. Right? Void star is a generic pointer, a raw memory address that can point to any type. Right? So why is it like this? Malloc is written like this. Is written to return a generic pointer, so you don't need multiple versions of it. Imagine if I did this for integers. I would need a malloc. If not, then you need a malloc for ints, right? You need a malloc for double. You need a malloc for char. When we start defining our own types, right, structures and stuff later on, you would need yet another malloc. In fact, you'd have to write that malloc. You need another malloc and another malloc and another malloc. We don't want to do that. We want one function to rule them all. That function is just regular old malloc. It doesn't return an integer pointer. It doesn't return a double pointer. It doesn't return a character pointer. It returns a pointer, period. Right? That's it. You use it however you want to use it. To use it, to ensure it points to the correct type, we typecast it. Typecast the returned pointer. So let's come over here to our example again. I want an integer pointer to point to my new array, int star array. If I simply made a call to malloc, this would work. It's better if you did this. Typecast the return pointer to match the type of pointer that you want. All right? You've done typecasting before. If I have int x is equal to 10 and int y is equal to 20, and I want to compute x divided by y, is that going to work? 10 divided by 20, what value does that have? Normally 0.5, yeah, but in this case, 0. Why? Integer truncation. How did we solve that problem? By making one of them a double. By typecasting it into a different type of variable. We're taking this void star pointer that's returned from malloc, and we're changing it into an integer pointer so that we have an integer array. Okay? What if we wanted a double array? Create an array, a dynamic array of doubles of, let's go with 1,000 doubles. There we go. How would I do that? Well, how would it look differently? Double star instead of an integer star. I can't use ARR again because that's already a variable used, so I'll go with BR instead, right? Right? B is one more than A, right? And I would typecast it as what? A double star. I would call malloc. How many of them do you want? Well, I'll put that into another variable here. Int m is equal to 1,000 so that I don't have to hard code that value. M times what? Size of double. There we go. Okay. In both of these cases, once you've got your array, you can use it like a regular old array, assuming that you've got your semicolons everywhere. Right? You can now treat ARR as a regular old array. I'll set the first value. Arrays of 0 is equal to 42. Arrays of n minus 1, setting the last value here, I'll set that equal to 101. Right? Likewise with BR. BR of 0 is going to be, I don't know, 2.5. Right? And set the last element. BR of m minus 1. I'll set that equal to 1.25. Right? Once you've dynamically allocated it and it's successful, you can treat it like a regular old array. I won't print these out, but let's go ahead and print out a couple of samples here. Arrays of 0 is equal to %d and the line, so arrays of 0, to show you that this actually works. And the last value here, last, is equal to n minus 1. Right? I won't bother with BR, but you could do something similar. No warnings at all. And guess what? It runs now. 5 million ain't nothing for the heap. 5 million, 20 million bytes, that's way too much for the stack. Right? But over here on the heap, you've got plenty of room. You've got unlimited memory. Right? Although, do you? 5 million. Let's see. 2.147 billion. 1, 2, 3, 1, 2, 3. I don't know if we can allocate that much. How much would that be? 2 billion times 4. Oh, that's nothing. What is that going to be? How much memory is that going to be? It's like 8 megs. Oh, no, it's too much. Too much. 2.147 million. 1, 2, 3, 1, 2, 3. All right, that's too much. 2 billion times 4. That's only 8 megs, or 8 gigabytes, right? I'm not sure why it's complaining about that. All right, fine. Whatever. GCC, 20 million is 5 million ain't nothing. 5 million, 50 million, 500 million? Okay, it's fine with 500 million. What about 1 billion? 1 billion should, times 4, that's 4 gigs, right? I'm just trying to break it and see what the limit is. All right, 4 gigs is fine. Why is 8 gigs not fine? Yeah, okay. 8 gigs is probably not fine because, well, we are piggybacking off of Harvard's CS50 here, and we're not paying for this. So I imagine that you do have an effective limit on these code instances. Right? Take it over to your own computer, though, and I'm sure that it would be just fine. In fact, I can show. I've got 16 gigabytes on my computer. Emacs test.c. Oops. vi test.c. Fine. Oh no. Quit. Vi foo.c. Okay, there we go. And I'll cut and paste my program here. Oops. And gcc foo.c. Now I'm running on my actual computer here, and I've got 16 gigs. There's no problem. There should be no problem with this whatsoever. Right. A.out. Yeah, there we go. So it is a limitation of your of our VS Code environment over here. They're probably throttling us at 8 gigabytes or something, right? But you can have as much memory as you want over here. That's fine. Right?
Is that memory on the disk or in your own?
Good question. That gets into computer architecture. Memory will be used as RAM, right? Well, actually, there's a whole memory hierarchy, right? Your processor has memory on it, right? Which is super fast, but it's super expensive. So you have primary memory, which is RAM, right? Less expensive, less fast, right? And then when you run out there, then you start writing to virtual memory, which is disk, right? That you can have essentially unlimited memory when it will just get written out to disk, and now it's super slow because if it's a traditional hard drive, now it's mechanical, right? If it's a solid state drive, it's going to be a little bit better. It's going to be definitely faster because there are no moving parts to it. But that all but solid state, I don't know, is this true anymore? Solid state usually is more expensive than regular old mechanical hard drive. That's still the case or not? Oh, it is? Okay, yeah. Is what?
It's gotten closer.
It's gotten closer to parity? Okay. Yeah, we're getting there. I don't know, maybe in 10 years you won't even be able to buy a mechanical hard drive anymore. Right? And if the memory, or if the cost is very, very comparable, I don't know why you'd buy one anyway right now, right? You can buy like a memory card RAID or something like that for really cheap. Right? All right. So what do you think happens if it fails? You can't have that much memory. Well, it resulted in a segmentation fault. But as far as the code goes, if you ask for too much memory or the system runs out, you hit a limit of some sort, malloc returns the only thing that it can. Right? Remember, malloc is returning a pointer. What is the only value of a pointer that says something went wrong? Null, exactly. Malloc returns null, which you can check for, right? Let me go ahead and change my program over here. So I asked for way too much, right? And before I test it, I look before I leap. I do some error checking. If array is equal to null, printf, oops, you asked for too much memory. We're out. Download more. ... There we go. And I'll exit on them, right? GCC, run this. If you asked for too much memory, we're out. Please download some more, right? Because it returned null, I check for null. I will remind you that, is this the proper way to do error handling? And if so, where do you do error handling like this? We are in the main. This is perfectly fine to do this in the main. Is this something you want to do in your functions, in your libraries? No, not at all. These are the two things that you do not do, right? Square root of -1 doesn't exit out of the program. It doesn't print anything, right? So when you go to do your hack, well, your lab today and your hack on Thursday, this is not how you should be doing error handling. You should be returning error codes from your functions. In the main, you're pretty much sunk. There's nothing else you can do. If you've run out of memory in main, that's a fatal error. Print an error message and then let it die. Right? That's perfectly fine to do it in the main. It is not fine to do it in functions. Right? Okay, just a reminder. By the way, we're noting that in your current hack 5, as we're grading, and we are seeing that in a couple of spots, but we're not taking off for it. Right? All right, so once you're done, let's keep track of bookkeeping first. Right? In C, you have what's called manual memory management. Right? It is your responsibility to ensure that you are not accessing invalid indices. Right? Keeping track of the size of the array, so you don't do the first one. Right? So you don't access invalid indices. You need to communicate to any function the size of the array, so it doesn't access invalid indices. And finally, you need to clean up after yourself. If you're done with your library books, what do? You return them so that somebody else can read them, right? You need to be good stewards of your resources on a computer. If you allocate memory, if you borrow memory, you've essentially checked that memory out, right? If you don't do anything with that memory, let me go ahead and get rid of this, right? Do something with ARR, Now we're done. Right? We need to clean up after ourselves. We need to take our memory and give it back to the operating system so that we're not wasting it, right? Now, it's not like if we don't give it back, right, we've stolen it. It's not going to stand up and walk away from the computer, right? Then you would have to download more RAM. But no, it doesn't work like that. When your program dies, all of the memory is reclaimed anyway and then reused. But if you've got a long-running program, for example, a web browser, imagine that a web browser kept, and this is too much, but 5 million. Imagine a web browser kept allocating 20 megabytes here, 20 megabytes there, 20 megabytes there, and it's running for hours on end because you're not closing it, right? It's a user program that doesn't get closed after a while, until after a couple of hours. Every few minutes, maybe it's allocating another 20 megabytes, another 20 megabytes, another 20 megabytes. What eventually happens if it doesn't give anything back? It's hoarding all this memory. Hopefully it crashes, but usually it just degrades the performance of the entire operating system because memory is being hoarded by one program and the other programs are starving, right? They can't run efficiently. It's being thrashed in and out of disk, right? Everything grinds to a halt. That's called a memory leak. If you don't free up memory and give it back to the operating system, it retains it, right? Once you're done, you need to free it up so that that your program or the operating system or another program can use it. Free array. Right? That's it. That's all you have to do. That's all you have to do to make sure that you're giving that memory back to the operating system. Right? What if you don't do it? Right? Let's run this program, GCC, and we've already seen that warning is irrelevant. Let's actually use it. ARR sub 0 is equal to 42, and ARR sub n minus 1 is equal to also 42. I don't care. Right? Now that warning goes away when I compile. Right? Okay. I've not freed my memory. I've hoarded it. If I were to do something else for a couple of hours here on this line, right, 16, right, then that memory is lost to the operating system. It's not apparent at all. Oops, that's not what I wanted. It's not apparent at all that there's an error because it runs without problems, right? And it's really quick. It only dies in the matter of a microsecond, right? I could time it. A dot out. It only took 0.002 seconds to execute, right? That's not that big of a deal. But if I ran this through Valgrind would detect that I'm doing something wrong. See that at the bottom? One error in one context. Let's read its report. Heap summary. Hey, I know what the heap is now. Right? In use at exit, 20 million bytes in one block. I wonder what that corresponds to. The 5 million times 4 bytes that I requested, right? And they were definitely lost. Right? They were lost because you never gave them back at any point. Now, the operating system, once it kills your program, it reclaims all that unused memory. Right? Again, it's not like going to walk away and disappear or be deleted or something like that. But it does become unavailable for any other program. If I did this over and over and over again, well, actually, before we do this over and over and over again, let's see the correct working program here. When I run this, again, same results, but when I run it through Valgrind, now my problems are solved. 0 errors from 0 contexts. No memory leaks. Okay? So let's go ahead and get rid of this. And let's not just do this once. Let's do this a lot. For int I equals 0, I is less than, I don't know, 1,000. I want it to, yeah, let's go 1,000, I plus plus. All right, there we go. And we'll do all this over and over and over again. Okay? Now, I don't want it to run really, really quick, so what I'm going to do is I'm going to make it sleep for 1 second at a time. Okay? This is just for demonstration purposes. Do not make your programs sleep, right? What you are literally doing is you're putting them to sleep, and they're not going to do anything for 1 second. Okay? So it's going to allocate this 20 million bytes, sleep for 1 second, allocate another 20 million bytes, sleep for 1 second, and it's going to do that for 1,000 times. 1,000. How many minutes is that? 1,000 seconds is, yeah, that's going to be like 18 minutes or something like that. Yeah. So we're going to be able to observe this in real time. So GCC, there we go. Oops. So I include, okay, fine. Can I run it? All right, yep. I'll run it. It's doing stuff in the background, sleeping, etc. What I want to do is I want to run it in the background, and then I want to look at it from the operating system perspective. Top is a utility that shows you that everything that's running on the system at the time. There's that A dot, oops, where is it? Come on. Oh, did it die already? No, oh no. It died? PS. Now it's running. Process 26878. I'm reading that right here. It's running. Let's take a look at it. Probably because it's sleeping. Then it comes back. Come on, where are you? All right, user Ubuntu. Where is it? We can't see it. Darn it. All right, fine. I'll go to a better system. I didn't like you anyway. I'm going to go to the CSE. And Emacs test2.c. I'm going to go ahead and cut and paste my program here. GCC test.c and a.out. There we go. So it is running in the background. I'll run it in the background so that I can actually look at a better, even better utility called htop here. That shows all the current system running processes. It also shows you this server down in Lincoln has 64 cores, and you can see what's running on any one core at any one time. It's not high usage here. Every so often you'll see something spike and you'll see its usage there. User Seberg. There we go. There's my a.out program down at the bottom. What I want you to pay attention to is this column right here. It's going up every second. 650 million megabytes. 730 megabytes. It's going up by increments of about 20 every 1 second or so. Right? Why? Because you keep allocating memory, never giving it back. Right? Eventually, you're going to run out. You are going to hit a system level system level limit where you're not allowed to allocate anymore. Right? But of course, this can run for 18 minutes here. At any one time, look at the total system memory right here. It has 126 gigs available to it. Does anybody's laptop have 126 gigs? Anybody's desktop have 126 gigs? Nobody wants to brag about that? Right. Can you fit that many DIMMs in a motherboard nowadays?
You gotta buy the expensive one.
Oh, an expensive motherboard. Okay. 512 gigabyte DIMM?
Yeah.
One DIMM. Wow. Price that out for me. That's got to be at least, what, $2,000? Yeah. Wow, okay. I have no idea what they're using down in Lincoln, but they've got 126 gigs available to us. So I want to make sure that I stop that process. I can list out the processes. There it is on the system here. It's process 10820. I'm going to go ahead and kill that. 10820. There we go. And it's been terminated. All the memory has now been reclaimed by the system, and that process has now been cleaned up. Let's take a look at the same process here, but let's be good stewards about our resources. Instead of grabbing more memory, hoarding it, grabbing more memory, hoarding it, grabbing more memory, hoarding it, let's go ahead and free it up every single time we do that. GCC. Yeah, go ahead.
The answer is $3,500 off of Amazon.
3,500 grand for a 512 gig DIMM. And what kind of motherboard would support a 512 gig DIMM in one slot? Many? Does it? Wow. All right. So yeah, you'd have to price that out and find out if you even have a motherboard that supports that. Wow. Anyway, let's go back to HTOP here. Now remember, this is the fixed program here. Take a look at it at the bottom there. Is it changing? There's the virtual memory. Only 24,000 kilobytes, which is about 24 megabytes. It's not changing at all. Why? Because when I allocate 20 million bytes, I immediately free it back up. Allocate it again, free it back up, allocate it again. I'm checking out the book, checking it back into the library, and back and forth, right? The memory footprint of this program now is not an issue, right? Because I'm being a good steward with my memory. I am freeing it up. You need to clean up after yourselves. Once you are done using dynamically allocated memory, free it up by calling the free function. Okay. And let's come back here to our coding environment. I'll go ahead and make sure that you have this example in your notes here, right? Except that we don't want that last free. There we go. I'll just do this chunk right here. Okay. All right. So that's what we mean by bookkeeping. You need to keep track of everything. If you're in a programming language like Python or Java or PHP or JavaScript or something like that, you are in a memory managed environment. The operating system or the interpreter or the Java virtual machine or whatever, those are responsible for taking care of all the memory. That if something is no longer needed, it automatically does what's called garbage collection. It sees it as garbage, sees that nobody's using it, goes and cleans it up. It reclaims it automatically. There's a price to pay for that. There's a severe price in some cases of efficiency. The fastest Python program will never beat the slowest C program. That's not true, but you get the idea, right? Right? Okay, so what else? Other pitfalls. More pitfalls. Right? Careful. Once you have freed memory, you cannot access it. Right? Attempts to do so will result in ... Let's find out. So I don't want to do this 1,000 times. So I'm just going to go ahead and get rid of the loop here and get rid of that and that. And let's go ahead and free it up responsibly. And then let's go ahead and try to print it out. Printf array sub 0 is equal to %d end the line. Let's go ahead and print out that first element. Array sub 0. Predict what's going to happen here. Well, first of all, I need to clean stuff up. We're still seeing bad indentation on a lot of submissions. So remind me, what tool can I use to correct my indentation automatically? A style, demo.c. There we go. And close this, open it back up, and guess what? Everything's fixed. Everything's nicely aligned now, right? All right. Predict what's going to happen here. You allocate 20 million bytes, okay? You do something with it. You're done with it. You free it back. You give back your library book. Oh, wait. I didn't mean to do that, right? I do need it still. What was that first element again? Right. GCC. Predict what's going to happen here. Yeah, they've already taken it back and they've given it out to somebody else. Can I access the library book if somebody else has it checked out? No. Likewise, I cannot access memory if it doesn't belong to me. If some other process is using it, segmentation fault. Right? That's illegal. Okay. Another thing that's illegal, so segmentation fault, result in a segmentation fault. The memory no longer belongs to you. Right? Careful. Only free something once. So, what if I did it, oops, cut, paste. I've done it now twice. Can you, you check out a library book. Can you check it in twice? It doesn't make any sense. Can you free something twice? Can you free something that doesn't belong to you? No. Segmentation fault. Right? We gave it back. The array, that 20 million bytes, no longer belongs to us. We can't free that up. That would be like saying, all right, I'm going to give back the library book. Somebody else checks it out, and I say, oh, you can take that library book back from them, right? No, it's theirs, right? You can't take it away from them. Somebody else owns it at that point. So this is called a double free. In fact, if I ran Valgrind on this, would it detect? Let's find out. There's an error. Yep, invalid free on line 18, right there. Sometimes it manifests itself as a double free error. That's not happening here. But you can only free something once. If you free it a second time without reallocating it, it is a double free error, right? And it results in a segmentation fault. Segmentation fault is just the generic catch-all term for something went bad, you did something wrong, right? Sometimes it's not something wrong. Sometimes it is actually a system-level error that occurred, but that's few. Those are extremely rare. Yeah.
Can you use the same array again after you freed it?
If you reallocate it, right? I freed it. I'm done with it. Oh well, I'm going to reuse the pointer, right? So array is equal to a new integer array of slightly smaller. I don't know, 1,000 integers, size of int. And then I can use it again. Array sub 0 is can't type today, sorry, is equal to 42. And I can print that out. Printf array sub 0 is equal to %d and line array sub 0. Right. This will execute without a problem. Right? But I'm not actually reusing the array. What I'm doing is I'm saying I made the pointer point to this 20 million bytes block. I freed it up. Right? Now that block is gone. On line 19, I'm making it point to a different block. And then I'm accessing it and I'm doing whatever I want with it. And then, of course, I should free it again, right, once you're done with it. Now, what we're going to be looking for in your hacks next week, of course, starting next week, when you start using dynamic memory, is if you're in main, you don't need to free it. Right? That's kind of like dealing with error handling in main. If there's an error in main, go ahead, quit. Make that fatal. You don't need to free something up in main. You do need to free it up elsewhere in your program, right? Because you are risking a memory leak. So if you write a function that allocates memory and it owns that memory, it needs to clean up after itself, right? Otherwise, once you return from that function, there's no way to clean up that memory. That's lost. That's called a dangling pointer. Right? You pointed to this memory over here, but then you came back and that memory no longer belongs to you, so the pointer is dangling here, pointing to what? I have no idea. There's no way to clean that memory up, right? Free it back up. So if you're in a function, you definitely need to do memory management. If you're in the main, don't worry about it. Right? Once your program dies, it'll be cleaned up anyway. Right? All right, any questions? Otherwise, we'll go ahead and look at that. We'll continue on this on Thursday.